Ya me está gustando más de lo normal. Esto hay que tomarlo sin ningún apuro. Despacito, quiero que sonara menos despacito. Firma las paredes de un laberinto. Descubierto tu manuscrito.
So our lead into our discussion on modern physics has been light, and the fact that light is a wave. It can be thought of as a wave because it does all the things that waves do. It reflects, it refracts, it diffracts, it has interference and Doppler effect and all of those things. But it also behaves like a particle under certain circumstances. That particle of light we call the photon, and it does things like collide with your electrons to knock them out of orbital shells. And in the example of the photoelectric effect, that light acting as a particle, those photons can collide with electrons and go across this tube to create some kind of current. And so we know that light is a particle as well as a wave, and that's what we call particle-wave duality. You can think of it one way or the other. But if photons are able to collide with things, classically, we had a very important thing that we talked about during our collisions discussion. It was this idea of conservation of momentum. And so let's look at this next topic where we apply conservation of momentum with these photons, just like we would have done with any two classical particles colliding. In 1923, Arthur Compton had this paper that he published on the Compton effect, which essentially had incoming X-rays that reflected off some material, and then you compared the incident frequencies with these reflected frequencies. And we found is that they weren't the same. And the only way that those frequencies would change was if there was a change in energy. And if there was a change in energy, that means the other bit of energy that we lost had to go somewhere, and that energy that we lost actually went into scattering electrons off of that material. And so if we have some kind of scattering or some kind of collision, we have to use conservation of energy and conservation of momentum, which implies that those photons coming in have to have some kind of momentum. But photons are just light. They don't have a mass. So we can't use just regular old P equals mv. It's not going to work. And so we need a new formula, which is the one shown right here, for photon momentum. So E is the energy of your photon, P is the momentum of that photon, and C is the speed of light. And so you can use this in your classical units, joules and kilogram meters per second, and the speed of light in meters per second. Or you could have your energy be in electron volts, your momentum be in electron volts per C, and your speed of light be in just C. And the value of using these relativistic units is then, for a photon, whatever energy you find is that same value for momentum, just with different units. If your energy is 100 electron volts, your momentum is 100 electron volts per C. As part of this paper, Arthur Compton found that there are a bunch of different scenarios. You could have the photon come in, pass right through, and end up at the other side without any kind of deflection at all. And that would be as if the photon didn't collide with anything. No transfer of energy, no transfer of momentum, it just passed right through. But there are other cases where the photon could have came in and then moved down at an angle, or moved down at a more extreme angle, or came in and then straight back out. So that's what's called backscattering. And all these different cases, the amount of energy that was transmitted and the amount of momentum that was transmitted depended on that angle of deflection. And so he related the incident wavelength with the scattered wavelength, and it depended on two other things, the material that you collided with and the angle for that collision. And so the formula is complicated, but looks like this. So you've got the wavelength of the scattered photon, which is in meters or nanometers if you're using your relativistic units. And so lambda prime is the wavelength of the photon after it hits and moves off somewhere else. Lambda is just going to be the wavelength of the incident photon, the one that came in. Then you've got lambda c, which is just a number, just a constant, 0.0024 nanometers or 2.4 times 10 to the 12th, depending on if you're using relativistic units or not. And that's different for different materials. This one is specifically for an electron. So the Compton wavelength of an electron is your 0.0024 nanometers. And then the last bit is just 1 minus cosine of phi, where phi is the scattering angle for your photon. It's the angle that the photon comes off with. So let's give this a try. Let's do a couple of different cases to see if we can get a handle of what Compton's formula is really doing for us. But that's going to be tough to do in Excel, so I guess we got to bring back the whiteboard. Let's start with the simplest case. We've got a photon that is coming in, and it's going to collide with this electron right here. I've put Compton's formula up top and also the Compton wavelength for an electron. And the simplest case is going to be if that scattering doesn't even happen. You've got some incident photon that comes in and just passes right through. So namely, if that phi term is just 0, if there's no scattering at all. So if we had lambda prime is equal to lambda plus lambda c times 1 minus cosine of 0, well, the cosine of 0 is just 1. And 1 minus 1 is going to give you 0. And so this whole term right here is going to disappear, and you're just left with lambda prime equals lambda. Or namely, your incident wavelength is equal to your scattered wavelength. And if those two are the same, there wasn't any scattering at all. It just passed straight through, no loss of energy. The other extreme case is when you have a scattering that comes right back at you, where this angle isn't 0, but the angle is instead 180. So let's give that one a try. So we're going to take our lambda prime and set it equal to our lambda plus lambda c times 1 minus the cosine of 180. But the cosine of 180, that's just minus 1. And so you're going to have 1 minus minus 1, and this will become lambda prime is equal to lambda plus 2 lambda c. And so if we wanted to find out this scattered wavelength, we just have to isolate that variable, and it'll be whatever we started with minus 2 times our Compton wavelength. And so that will be the wavelength for our scattered photon. Whatever we had initially, minus 2 Compton wavelengths will give us that scattered wavelength. But what you'll notice is that if it came right back at us, it had to go back this way. And if momentum is conserved, that means the electron had to be kicked out that way and go straight into the screen. If we had a more complicated thing going on, what if we had photon come in and collide down this way? To conserve momentum, that means the electron would have to go up that way, and we'd see that both of them have an x and a y component, so we have to break things into components and do all sorts of fun algebra, and that's the plan right now. So here's the plan. We have some incident photon with a wavelength of 0.14 nanometers, and it's going to collide with this electron and kick the electron out into like the first quadrant. It's itself going to get scattered down to the fourth quadrant at some angle of 30 degrees below the horizontal. What we want to do is we want to figure out this momentum by finding this wavelength first, and then we can use conservation of momentum to figure out what that angle is up there. So our ultimate goal is to figure out what angle the electron's kicked out with. Let's see if we can do it. We just have to figure out this photon's scattered wavelength, and we're just going to use Compton's formula. So lambda prime equals lambda plus lambda c times 1 minus cosine of phi. Really no reason to rewrite that because I have it up there, but whatever. And so what we're trying to find is this lambda prime. So we're going to plug in. Our initial lambda, our incident wavelength, is 0.14. We're adding to that our Compton wavelength, which is just a constant, 0.0024 times 1 minus the cosine of 30. Sweet. So this is a number, multiply by another number, add to another number. Calculators can handle that, no problem. And hopefully what you'll find is that at the end of this, it's 0.1403 and still in nanometers. I left all of our wavelengths in nanometers. And so wavelength went up, which is hopefully what you'd expect, because as wavelength goes up, frequency must go down. And as frequency goes down, energy does as well from E equals HF, which is our formula for energy for a photon. And that should make sense because some of that energy had to go to the electron to kick it out as well. In fact, if we knew the incident photon's energy and the scattered photon's energy, we could get the energy for that electron. So let's try and do that next. I've got some formulas up here. These are just our energy formulas. It's E equals HF. I've just replaced the F with the speed of light over wavelength. That's just our wave speed equation, so I'm able to do that. And now we just plug in. H is a constant. It's our 4.14 times 10 to the minus 15 electron volt seconds. So our energy at the end of this is going to be in electron volts. And so it's just going to be that number times our speed of light, 3 e to the 8, and then divided by our incident wavelength, which is 0.14 nanometers, which I'll write in as 0.14 e to the minus 9. And then you do the same thing for the other one. E to the minus 15, 3 e to the 8, and we divide by our scattered wavelength, which is 0.1403 e to the minus 9. And hopefully what we'll get is an incident energy that's greater than our scattered energy. In fact, my calculator over here says that this one is 8,871 electron volts, and the scattered one is 8,851. So those are our two energies. We came in with 8,871 electron volts. We scattered down with 8,851 electron volts. And so that means the electron is going to get the difference between those two. So maybe I'll rewrite this as E with a subscript of little e for the energy of the electron. And it just gets what's left over from 8,871 minus 8,851. So 765, I think that's like 20 electron volts of energy for that electron. Okay, just doing a little tidying up here. I just moved the energies over here for the incident photon and the scattered photon and our electron as well. And so the next step on our journey, so we've got all these energies, so we know the incident, scattered, and electrons' energies, and now we need to figure out their momentums. And this is where relativistic units are actually really, really nice, because we had our formula that Compton gave us, which is that E, this marker would work, E equals PC. Make that look more like a P. All right, so energy is equal to PC. We could just use relativistic units that say that our momentum is in units of EV per C. And so all that means is that this number is exactly the same, it's just divided by C. So P lambda is just going to be 8,871 EV per C. P lambda prime is just going to be 8,851 EV per C. And then PE is going to be, this is not a photon, so we can't play the same game anymore. This is going to take a little bit of extra work using conservation of momentum. And so what we have to do is we have to think about what momentums are going on in here. Initially, the electron's not moving. That's the thing that gets collided into, so it doesn't have any momentum at all. Initially, the only thing with momentum is this incoming photon, which is traveling to the right. So all of our initial momentum is to the right. After the collision, the electron has momentum to the right and up, and the photon has momentum to the right and down. So we need to relate momentum initially with momentum after, and they have to follow those two rules. Our initial momentum has to equal our final momentum, and that must be true for the x. P initial x has to equal P final x. And it has to be true for the y. P initial y is equal to P final y. So we have to make sure that those two things agree. It's the only way we're going to be able to solve this problem. So this is our plan. We have to figure out what the initial and final momentums were in the x and y direction. So let's start with the x direction. Initially, the only thing with momentum was our photon. And so our initial momentum, I'm going to write in as P with a subscript lambda. So it's just this value is what we started with. After the collision, both of these things have momentum. And so that's going to be equal to P lambda prime x. So this photon, the scattered photon's x component, and then plus PEX, the electron's x component, because they're both moving to the right, or, part of their motion is to the right. And so that's the x direction stuff. Now in the y direction, we didn't have any y component of momentum in the beginning. So this is just 0. Afterwards, the electron has a component and the photon, the scattered photon, has a component. So we can say P lambda prime y plus P E y. And so if you'd like, P E y is equal to negative P lambda prime y. And so we've got two expressions for these momentums. And they look a little bit daunting, but really, this is a number that we already found. This is just finding a component, which we've been doing for months and months and months now. And then this is just finding a component, which we've done for months and months and months now. So let's just, on the side here, just write in what those components would be. P lambda prime x is just going to be P lambda prime cosine of 30. The x component is just going to be the adjacent side of this triangle with an angle of 30. And P lambda prime y is just going to be p lambda prime times the sine of 30. Ain't no thing. So we can just plug those in, and we would have expressions that would look like PEX is equal to P lambda minus P lambda prime x, and then this one's already set for our electrons y component as well. So PEX is going to be P lambda, which I said is 8,871, minus the x component for our scattered photon, which I've calculated to be 7,665. And so PEX is just going to be 1,206 electron volts per C. And this one over here, PEY, is just going to be 4,425 electron volts per C. And this one should be positive because it goes above that x-axis. So technically speaking, the y component of lambda prime is negative because it goes below that x-axis. And so here we go. We've got two components of that momentum. And the way that you're going to find that total momentum is to just combine those two vector components. PE squared is equal to PEX squared plus PEY squared. And so at the end of this whole game, once you've done this algebra, you'll find that PE should be 4,587 electron volts per C. So very different than if we just took the difference between those two. So that's our momentum for that scattered electron. The last thing that you may want to do is you may want to just find the angle for this thing. And my favorite way to find that angle is just going to be the inverse tangent of PEY over PEX. So our tangent is opposite over adjacent. And so if I turn that into a shell real quick, degrees that's much better. 75 degrees. .75 degrees of deflection. Alrighty, that's a process, but thankfully all these Compton problems are the same. So in general, you're going to be given some initial wavelength for your incident photon, and you're going to be given the photon's angle. You need to be given the photon's angle because that's how you use the Compton formula. So the first step is to find out what that scattered wavelength is. Not a problem, we're just plugging into that formula. Then we have to find these energies, and that's just going to be hc over lambda, using our incident wavelength and our scattered wavelength. And then you can find the energy for your electron by just taking that difference. Then we need to find the momentum for our incoming and outgoing photons, and they're just the same value, but in units of eV per C. That's a nice thing about these relativistic units. You can't play the same thing with an electron though, because it's not a photon, and so it has some mass, and this formula doesn't really work What you have to instead use is conservation of momentum. You have to break the momentum into x and y components, make these formulas, and this is always going to be the case that you're going to have your incident photon is equal to the scattered photons x plus the electrons x, and then nothing is equal to the scattered photons y plus the electrons y. You can't really have something going on in the beginning, otherwise you'd have a way more complicated problem. I guess you could, but I wouldn't do that too. And so then you just work through this algebra to get down to the two components for the electron's momentum, use a little Pythagoras, and then find that angle using arctan. And it's just going to be that same process every time. So that's a Compton problem. So that's the Compton effect, or Compton scattering. It is kind of a long process through algebra, but the basic idea of it is that it's another piece of evidence that photons can be treated like particles. You've got some incoming photon which collides with an electron, and they both scatter out, and we can further prove that they're acting like particles because they use the same classical physics that we've already used for collisions, conservation of momentum. And so this is kind of the end of the trail for our discussion on photons. We've covered a bunch of ways that photons interact with matter. We just talked about the Compton effect, which very simply is that a photon can be scattered off of an electron, or really any other particle. We just use the electron because it's easiest. And that's going to result in a decrease in energy, namely frequency, for that photon. We also talked about the photoelectric effect last time. The photon can knock an electron out of an atom, and then that photon kind of disappears in the process because that energy gets absorbed by the electron. In a video before that, we talked about emission and absorption. The photons are absorbed by the electron that's bound to an atom as it moves up to some higher orbital shell, and then emitted as it falls back down. The last weird thing that photons can do is this thing called pair production. So if a photon has enough energy, it will actually dissolve. It'll break apart into an electron and a positron. An electron is just the same particle that we know and love, and the positron is the same exact thing, but with a positive charge. And similarly, this process can work in reverse. If you have an electron and a positron, and they come together, if they collide, they're going to transform. You'll no longer have your electron and your positron. You'll have one single particle, the photon. And so these are the 4 ways that photons interact with matter, and that's going to be the end of our discussion on photons. All the way back with particle-wave duality, we didn't even think of photons at all. We thought light was a wave, and that was the end of the story. But really, there's many different ways that light has shown that it can be treated like a particle. And that's the principle of complementarity. That was something that Niels Bohr came up with in 1927. Light isn't a wave or a particle, it's both. And you have to think of it as both, and really you're just setting up experiments to look at it as one thing or the other. This idea of particle-wave duality, though, we've kind of only looked at it from one side. We've shown that light, which is a wave, or at least so we thought, can be thought of as a particle. There's got to be some way then, if there's a duality, that our particles that we know of can be treated like waves, and that's going to be our discussion tomorrow.